And our next speaker is Bobin from Polygon. There you are.
Thank you. Hey, everyone. Very excited to be here. All right. So my talk today is about Maiden VM. This is the heart of Polygon Maiden rollup. I will actually not talk a lot about the actual rollup aspects of this. Polygon Maiden VM is kind of general purpose, and you can run many rollups with it. The way it works actually is like you can deploy different OS on this, and the OS defines what the rollup is. So like things like UTXOs I'm very excited about, but they're not actually encoded in the VM itself. This is something that could encode in the OS that runs on it. And so like Polygon Maiden OS, the one that runs the rollup is the one that determines like the structure of the rollup and all of that. But I did, before kind of going into details of Polygon Maiden, I want to give an introduction of what the ZK-VM is, and probably it's familiar to most of you, but I think it's good to set the context. So let's start with a regular VM. Regular VM basically is just a state machine where you start with some state, you apply some program to the state, you execute something, and then you get the output state. This is like a very, very basic thing. With the ZK-VM, we get a couple more boxes here. So one of the boxes is you also get the proof of execution at the end. So as you execute some program, at the end you get this proof, and nobody else needs to execute this program again. They just like verify the proof and know that this set of inputs, if you apply this program, will lead to this set of outputs. The other thing that we get is that something called witness or private inputs. So you don't have to necessarily, it could be private data that you don't want to reveal, some secret to whoever needs to verify the program execution, or it could be something that you use for compression. As an example, you can probably, let's say this is a transaction that you are executing, and as part of the transaction, you need to verify a signature. So one of the nice things is that you could provide transaction or signature as part of the witness, and then nobody else needs to like actually verify the signature. They just verify the proof. Signature is already verified for them as part of this proof. And then, we can do some kinds of optimizations. We like frequently don't actually need to provide the full set of inputs and the full set of outputs as part of the inputs or even the program itself. We just provide commitments to the inputs, to the outputs, and to the program, and provide the actual state, the input and output states, and the program code via this witness. This allows us to compress things even more, like you only provide 32 bytes for a given program, for example. And that's, that describes the entire program because everything else is provided non-deterministically through the witness. All right. One very important aspect is proof is very fast to verify. It doesn't matter almost how long the execution takes of the actual program. The proof takes exponentially less time to verify. It takes much more time to create, so like the proving is costly, but the verification is cheap. So you can run the VM for 1,000 cycles, or for 1,000,000 cycles, or even maybe for 1 billion cycles, although for that you need a lot of memory. But let's say, regardless of how long the actual execution takes, the difference in verifying the proof is going to be very small. Like you could verify one proof in 1 millisecond, the other one in 2 milliseconds, and maybe, like the other one would be in like 2.5 milliseconds or whatever. So it's like really talking about milliseconds here for verifying almost arbitrary length computations. All right, one of the things that we want to answer, like when we build a ZK VM, or I guess any VM in general, is what instruction set we want to support, what we're going to want to go with. So like one option is like choose something mainstream, RISC-V, or you can choose WebAssembly. The other one you can say, we're going to be EVM equivalent. And then the other one is like we can build something that's ZK optimized, or you can say maybe specifically optimized for some other use case. And then there are a set of trade-offs that come with each choice. So for example, if you choose tooling, if you go with something that is mainstream, you have a ton of tools available. There is like, for Rust, WebAssembly, RISC-V, you have the entire tool chains built out already. If you go with EVM equivalents, you have already a lot of tools. Like it's not as many or it's not as rich of an ecosystem as for traditional languages or widely adopted languages, but it is, it's there. You have Foundry, Truffle, whatever, like a bunch of different tools. And then if you go with something that you build yourself, obviously you have you have to build everything from scratch. The other one is like do you go with something that is blockchain focused? And this is like an interesting thing because if you go with RISC-V or WASM, this is obviously not blockchain focused. They need to do extra things to make sure they work well in the context of a blockchain. There needs to be some modifications. If you go with EVM equivalents, obviously this is already blockchain focused by definition. And then if you're building your own thing, you can also define like the parameters and make it blockchain focused as much as you want. And then this is specifically performance in the context of ZK, how easy it is to generate proofs. So for mainstream, it depends on which instruction set you go with. For something like RISC-V, maybe it's more efficient. Like if you try to do x86, it's like going to be very inefficient. RISC-V may be a bit more efficient. WASM is somewhere in the middle probably. But generally, those instruction sets were not built for ZK friendliness, so it's going to be a bit more costly to generate proofs. EVM was not built for ZK friendliness, and at Polygon we have ZK EVM, which does generate proofs, but it is, obviously the computations are costly, so it's not something that you would be able to run in a browser or on a mobile device, at least not anytime soon. And then lastly, if you're building your own instruction sets, you're free to optimize as much as you want. All right, so a quick overview of Maiden VM. First, I want to say, like, what are the things that we wanted to achieve with Maiden VM? So first, kind of table stakes in a kind of smart contract world or regular world, but in the ZK, it's a big deal. Like, build something that is Turing complete. Basically, you can execute any program. Frequently, especially in a circuit model, you're limited. You can't execute arbitrary programs. You have to account for the upper end or whatever, the worst case, and then you build your circuit for that. But we wanted to have something that is Turing complete. The second one is we want to have something blockchain focused. So we designed ISA specifically that targets use cases or optimizes for things that are relevant for blockchains. And I'll list some of the examples later, I think. But one of the things like verifying Merkle proofs should be efficient, hashing should be efficient, like some certain operations should be efficient, and so forth. So we gave priority to those. We built this for ZK friendliness, so we designed specifically the instruction set and operations so we can prove them easily in the ZK context. Our proofs are very efficient. You can execute. I mean, I'll show some performance numbers. The ZK VMs are still much slower than regular VMs, but as far as the ZK VMs go, Maiden is pretty efficient. One of the core goals for us, and this also will bleed into the next point that I'll make, is safe composability. What I want to mention by this is that you can execute untrusted programs. So, and actually let me show the next one. So we want to have, like, one of the goals for Maiden rollup, and therefore it bleeds into Maiden VM design, is that we want to have privacy. And to have privacy, you need to execute programs that the blockchain operator or the block producer does not have any concept about. They are private. People kind of define them and just put a commitment on chain. So you need to be able to execute programs that are not known, or at least verify their execution. And therefore, we want to make sure that you can compose programs that you have no idea what they do with programs that you do know what they do, and it doesn't break anything. Like, you don't write in the wrong place in the storage, or it doesn't break some invariance. So very important part of the Maiden design is the safe composability, where you have execution context and you can execute something in a private context, and then it can have some interface to the public context and so forth. So that's one of the main design goals. To go over some high-level components, and I'm not going to go too much into details, but Maiden is stack machine, so you have an operand stack very similar to EVM. It has its pluses and minuses. Register machines are more efficient in some ways. Stack machines are easier to encode instructions. In the ZK context, there's other options, but we decided to go with a stack machine. We have memory, read-write memory that is accessible. Again, not a big deal for your usual machines, but in the ZK context, sometimes you could implement write-once memory, and it's much more efficient for ZK context. This is read-write memory. It's a bit more constraints, a bit more complicated, but we decided that it's needed because people are more used to this memory model than to a write-once model. The other thing we did is, we have this set of chiplets, and this is important if we think about circuit versus VM-based execution in the ZK context. Circuits are going to be much more efficient by design because you only create a circuit for what you need. VM, you have some overhead, but the way you deal with overhead is you create these chiplets that is a specialized accelerators for specific circuits, and you can accelerate hashing, you can accelerate signatures, and so forth. So we have a set of chiplets that we expose in the VM. And then one other cool thing that we have is that there is an interaction between the host and the actual VM. And the host is like an environment that you can define as part of like regular kind of computer or whatever that you're executing a regular program. One nice advantage of ZK virtual machines is that you can provide this non-deterministic inputs via the host. So you can offload a lot of computations to the host. And what I mean by that is if there is a computation that is much more efficient to verify than to compute, then you can perform the actual computation in the host and then ask the VM to verify it. An example of this could be like square root, for example. Square root by itself is a fairly complicated computation, but you can compute square root in the machine code very optimized and then give the result back to the VM, and the VM just needs to do a multiplication to verify that square root was computed correctly. So that allows us to simplify a lot of computations. OK, I'm going to skip this. I think this is one of the things I want to cover. So we want to have Maiden VM to support many different languages. The way we've designed this is that we have Maiden assembly, and there is a Maiden assembler that does it, compiles Maiden assembly to kind of the code that gets executed in the VM. Maiden assembly is not pretty to write in, like it's not nice, and we don't want people to do it. So we're building a toolchain. For example, right now we're building the compilation from Rust. So we want people to be able to write Rust, compile it to WebAssembly, and then WebAssembly gets compiled to Maiden assembly, and that gets executed on the VM. We already kind of have a compiler working from WebAssembly to Maiden assembly. We're still working on the Rust part. But we want to make it more general. There is actually other languages that we could plug in. Like I'm a big fan of Sway language, for example, and I would love it to also run on Maiden VM at some point. And you can plug in there, like if you can compile to WebAssembly in specified format, you will be able to execute it on Maiden VM. If you can compile it directly to Maiden assembly, there's actually intermediate representation that I didn't show that is kind of crane lift based. You can compile to that, and it also will be executed by Maiden VM. So we want to be support many different languages on Maiden VM. And yeah, I'll skip that one because I think I'm out of time. But this is kind of performance, and you can see that it doesn't run that fast, but it is good enough to generate most transactions, and then we're working on optimizing this. All right. I think I'm out of time. Thank you.
Thank you. Do we have some questions? If not, then you can just keep talking. OK.
Can we compile circum circuits to this?
It's not designed for that. You would not necessarily want to do circum. So the whole idea of the VM is that you don't need to design circuits. So I would say you would either do circum circuits or you would use Maiden or something like that, because those are two alternative paths. Circum, I mean, you could do it. It probably would not be the best idea to do it.
Any other questions? We should just get you your own microphone. No?
So quick question. So if you go to slide one slide back.
Let me see.
OK. So
I don't know.
No worries. So my question is, because Polygon also has a ZK VM, right?
Yes.
So what's the performance gap between, because you're building a next ZK VM. So what's the performance delta in there?
So so the applications are different, and the kind of execution models are different. So ZK VM, you are expected to be executed on a big server. So like right now, we are running ZK VM on a server with 128 cores and half a terabyte of RAM and things like that. So this is the purpose, how you would run ZK VM, because you have the 256-bit arithmetic to deal with, you have cache and all of that stuff that is not very ZK friendly. Maiden is designed to be run basically on a laptop or a smartphone. So right now we can run most transactions for Maiden on a simple laptop. We estimate that for most transactions you probably don't need to have more than between 4 and 8 gigabytes of RAM to execute them, you should be able to do it at least for now on a let's say 6 or 8 core laptop. You should be able to do it in under couple seconds. Again, it's not quite apples to apples comparison because like you can say, okay, well, what if I like break out EVM transaction to be like a single transaction, try to execute it? Maybe it would be like 10x less efficient, but you can't do it with EVM because like EVM is a global state and that's like part of the UTXO. You can't individually prove every EVM transaction and then combine them together. You have to like have a single block that because of like interdependencies between transactions. Maiden is slightly different, like where you can execute each transaction individually, and it should be like our goal is to do it. At least for now, you should be able to do it on a laptop, and maybe in like a year or two, you should be able to do it on a smartphone as well. You combine them using recursive proof aggregation. Yeah.
I got one more question for you.
Yes. I have a different talk at a different event where I explain how that would work.
Quick question: is this can you illustrate the difference between a Maiden and Polygon 0?
Well, Polygon 0 is a prover, right? So Polygon 0 is a prover that we're building for the POS chain. So they're different. So Maiden is its own VM. Polygon 0 is the proving system, like Plonky 3, for example, which Maiden probably will use in the future. So they're kind of different parts of the stack, so to say.
But the 0 can be used to prove Maiden as well as the Hermes.
So Plonky 3 we would be able to use Plonky 3 that is developed by Polygon 0 to prove Maiden execution, same as EVM execution. So it's the backend prover that is responsible for actually generating proofs. It's not the instruction set of the VM. So you could use Plonky 3, for example, for proving EVM or proving Maiden and whatnot. Maiden is like a VM that rides on top of it. So Polygon 0, it's not its separate VM.
And maybe just sort of a general question on Polygon, but you've got all these different solutions out there. How are they supposed to all accrue value to the Matic holders, token holders, if you will? Yeah.
So I mean, we have this vision of unified kind of ecosystem of chains where you can run different chains. Like Maiden would be one chain, ZK EVM is another chain, POS, and then other third-party chains, so to say, that can plug into that. All of them will use some part of there's staking hub through which people may choose to validate or add security to their chains, or there could be some fees that depending on which parts of the security model you use, you could contribute to the kind of Matic and things like that. So through that aggregation, Maiden doesn't have its own token or anything. So through that kind of aggregation, using shared proving and shared how should I say, staking kind of hub, that's how it would accrue back to Matic.
Thank you, Bobin. Give him a round of applause, please.
Thank you.
Thanks, man.